So I'm going to talk to you today about LEAP. And you may have heard about LEAP recently. It's been one of our recent successes in the Space Science Center, although at this point it's kind of a partial success. It is a project that I am currently leading, a major collaborative effort. You see here the logos in this view of the major institutions, which include NASA Marshall Space Flight Center in Huntsville, the University of Alabama in Huntsville, of course, UNH and Southwest Research, and also Teledyne Brown, which is our commercial partner in this endeavor. So let me see. Okay, so why? Oh, there we go. So the outline of my talk today, I'm not going to go into a lot of technical detail, but enough to give you an idea of what LEAP is all about. I want to make sure I talk a bit about gamma ray bursts for those of you who may not be all that familiar with what they are all about, because those are the primary targets of the LEAP mission. So I'll then talk about the LEAP mission itself and the hardware, the fact that one thing that's probably obvious from the previous slide is the fact that it is an instrument that will be mounted on the ISS. So I'll talk a little bit about the technical issues there, and then finally end up talking about the LEAP science objectives and what we hope to accomplish and the measurements that we hope to make. So gamma ray bursts. Gamma ray bursts were first recorded back in 1967 by the Vela satellites. These are satellites put up in part to monitor for atmospheric nuclear detonations as part of the Nuclear Test Ban Treaty. I don't know if they ever recorded any nuclear detonations, but we do know that they recorded flashes of gamma rays, very intense bursts of gamma rays, that were determined to originate somewhere outside of the Earth. And here you see a time history of one of the early gamma ray bursts. You can see here that on a time scale of a few seconds, the instrument counting rate went up from a background level of maybe 100 counts per second to something approaching 1,500 counts per second. So these are very intense flashes of gamma rays. There were a few instruments over the years that investigated them. One of the big breakthroughs came, however, with the Compton Gamma Ray Observatory in the 1990s. It was launched in 1991 and lasted until 2000. There was one instrument on the observatory that was dedicated to the study of gamma ray bursts, and that's an instrument called BATSI. The Burst and Transient Spectroscopic Explorer, which consisted in this view of the observatory being deployed from the shuttle. The BATSI instrument consisted of 8 detectors, one on each corner of the spacecraft. And by looking at the relative counting rates in these 4 detectors, we were able, or the BATSI team was able to determine the direction of a gamma ray burst within a few degrees. I will point out here that this instrument in the center is the COMPTEL instrument that UNH was involved with as part of that mission. But the BATSI instrument collected data on several thousand gamma ray bursts. They saw them on average once every day or two. You see here a sampling of time histories of some of those gamma ray bursts, ranging in duration from a fraction of a second here in the lower left, to some that are several tens of seconds or even hundreds of seconds long. It has often been noted that if you've seen one gamma ray burst, you've seen one gamma ray burst, that they are all very different from one another, kind of, if you will, kind of like cosmic snowflakes. A typical energy spectrum for the gamma ray burst looks like what you see here on the left. The upper left here shows the flux of gamma ray photons extending over a range of energies from about 10 keV up to several MeV. If we take this spectrum and plot it on an E², sort of a logarithmic scale here, you see that the peak power output of a gamma ray burst occurs in this particular case at about 1 MeV. And we refer to this, this peak energy here as the peak energy. It's a characteristic energy of the energy spectrum. And that peak energy, typically, if you look at a distribution of several gamma ray bursts, is typically in between 100 keV and a few hundred keV in energy. So one of the early questions we had was how far away are these gamma ray bursts? Again, these are very intense flashes of gamma rays. You can sort of think of in the gamma ray realm, a gamma ray burst really lights up the sky. But early on, it was hard to really study these objects because they would go off, they'd last a few seconds, which didn't really give us enough time to really determine or pinpoint their location on the sky, or to take other instruments to train them on the source to see exactly what was going on. So there was this big debate about whether the gamma ray bursts lied within our galaxy or if they were something external to our galaxy. Or even some of the early ideas, talked about whether gamma ray bursts perhaps were some kind of weird population of objects within our solar system. So we didn't know the fundamental question of how far away they were. The BATSI instrument on the Compton Gamma Ray Observatory, as I mentioned earlier, was able to determine crude directions or crude locations for these sources. So and these sources, I should add, they pop up randomly in space. They don't always come from the same direction. They don't seem to repeat. So they occur both randomly in space and in time. So it was thought early on that if we could measure the spatial distribution of these objects on the sky, that maybe we could get a handle on how far away they were. For example, if they were a population of objects lying within our galaxy, we would expect that they would follow a distribution which sort of mimicked the distribution of the Milky Way in the sky. So we would sort of expect that the gamma ray burst plotted here in galactic coordinates, if they were within our galaxy and a phenomenon within our galaxy, they would map out with a distribution that lied along the galactic plane. So many of us at the time, and I thoroughly remember this period of time, this period of uncertainty, we're thinking, oh, these gamma ray bursts are probably like some super flare kind of thing, a super stellar flare or something. And so we fully expected that, or at least some of us fully expected, that we would see, if we took the BATSI data, we would see a distribution on the sky that looked like this. Well, turns out that very early on in the GRO mission, BATSI had their first results, and this is sort of an assembly. I think there's about 3,000 bursts or something like that contained in this plot. And this is a result from BATSI made over many years. And the distribution on the sky turns out to be incredibly isotropic. And so this really argued very strongly against the idea that these were some sort of galactic phenomena, and that these objects were in fact extragalactic. But we still didn't really have, there were still people who argued, well, maybe there's something that are really local within the galaxy, or maybe at the the heliopause maybe, or something like that, such that they were so local that they still appeared isotropic. So it really wasn't a definitive answer. One of the other clues, and I'll mention this now, but I'll come back to it in a little bit. One of the other clues was that if you look at the duration of gamma ray bursts, they range in duration from, a fraction of a second up to several hundreds of seconds. But if you look at the distribution of burst durations for a large sample of gamma ray burst, you see this kind of a distribution. It appears to be bimodal. And so we started talking about gamma ray bursts that were short, less than about 2 seconds, which is right around here, and long gamma ray bursts, which were more common, but those were the ones that were longer than 2 seconds. I'll point that out now, and as you'll see, we believe that these represent 2 different populations of gamma ray bursts. So in summary, the sort of GRO era back around the year 2000 or the mid-1990s, say, the observable characteristics could be summarized as follows: intense flashes of gamma ray emission, typical durations of less than 100 seconds, some exceptions, but typically. They're random in time, isotropically distributed on the sky. Most of the energy was emitted between 100 and 300 keV, roughly. And if you looked at the duration distribution, it showed a bimodal characteristic. The first, a big breakthrough came in 1997. Instruments on orbit were becoming more sophisticated. The goal was to catch a gamma ray burst in action, to be able to define and identify the precise direction of a gamma ray burst. And it just so happens that there was an X-ray satellite called Beppo-SAX, an Italian X-ray satellite. SAX is some Italian acronym. Beppo refers to a very famous Italian astronomer whose name I don't remember, but nonetheless, it's commonly referred to as Beppo-SAX. And it had X-ray instruments that recorded, as you can see here, the location of a gamma ray burst. And the image on the left was taken 8 hours after the gamma ray burst. And so there was an afterglow. And this was the sort of thing that astronomers we'd been looking for years, trying to get this kind of a data. And in 1997, we finally had it. We could take these X-ray data and really pinpoint the location of the gamma ray burst. And then with that location, we could follow up with observations with other types of instruments. And so here, in fact, is a follow-up observation made of that gamma ray burst by Hubble Space Telescope. And so this is, in some very real sense, it's a little bit astounding. Okay, so here on the left, you've got an image from Hubble. There's a lot of noise in this image. So you really, it's sort of like reading a medical X-ray. You really need to know what you're looking at to see this kind of thing. But right here, this little bright spot here, which is now blown up here on the right, this pixel, this single pixel, was determined to be the gamma ray burst. And in fact, they could follow it up with a series of observations, and they saw it decaying. So they determined that this was indeed the location of a gamma ray burst. Furthermore, this fuzz, if you will, was determined to be, or interpreted to be, the host galaxy of that gamma ray burst. So if one says that this is the host galaxy of the gamma ray burst, and then you could go and you could measure the redshift of this galaxy and infer from that how far away the gamma ray burst was. And it turned out that that redshift measurement, placed it at 6 billion light years away. So clearly, this was kind of the nail in the coffin, if you will, for the galactic idea, the galactic origin for gamma ray burst. And from that, we concluded that GRBs are clearly at extragalactic distances. And in fact, this particular figure comes from 2009. It shows a distribution of redshifts to gamma ray burst. And it turns out that gamma ray bursts are some of the most distant objects in the universe. And in fact, at the time of the observation of this particular gamma ray burst, 090423, which took place on April 23rd of 2009, at that time, the redshift for that object indicated that this was the most distant object that we had ever measured. Now, since that time, there are, by the list I looked up the other day, there are only 5 known objects more distant than this particular gamma ray burst. So these are indeed some of the most distant objects that we know of. And therefore, some of the most energetic objects that we know of. The long versus short gamma ray burst distribution, I wanted to come back to that because it turns out that if you look very carefully, and again, you have to look a little bit with trained eyes here and maybe squint and maybe think really hard or really, you got to really imagine it, if you will. At the top are some images of long duration GRB locations. At the bottom are short GRB locations. And it turns out the long GRBs tend to be associated with active star forming regions. So that sort of implies, for those of you familiar with stellar evolution, it implies fairly massive objects, or if they're taking place within a region of active star formation, they're somehow associated with massive stars. The short duration gamma ray burst appeared to be associated with a variety of different environments. There was no clear, that you couldn't say they were all associated with some particular environment. So they were sort of like a hodgepodge, if you will. So what came out of that were 2 models, 2 generalized models for the origin of gamma ray bursts. Long gamma ray burst, we believe, are associated with very massive supernovae. In other words, supernovae associated with stars of 50, 60, 70 solar masses, releasing a huge amount of energy, temporarily leading to an accretion disk, out of which, along the rotation axis of that accretion disk, you have a jet of emission. And if that jet happens to be pointed in our direction, we see that as a gamma ray burst. It's a transient accretion disk, a transient jet, survives for a few seconds, and then it's gone. And what you're left with in that case is a black hole. The other scenario for short gamma ray bursts is that you have a binary compact star system. And as the binary system loses energy and those 2 compact objects coalesce, you end up once again with a transient accretion disk, which generates and leads to a beam of radiation, much like the long gamma ray burst model. But in this case, you have 2 compact objects merging to become a black hole. So 2 different scenarios, each of which creates a beam of radiation, which when directed towards us, we see as a gamma ray burst, and both of which lead to the formation of a black hole. And this is essentially repeating the same thing. Here you have the merger scenario here on the upper left, the lower left, you have the so-called hypernova scenario, very massive star, both of which lead to jets of material or radiation emanating from the central engine. And again, if that jet points towards us, we see that as a gamma ray burst. And the gamma rays are originating somewhere towards the base of this jet. And as that jet interacts with the surrounding interstellar medium, we get X-rays, visible light, radio waves. This is what creates then the afterglow that we have been able to observe for hours or days or even weeks in some cases now. So the other interesting feature is that the merger theory may sound familiar if you're familiar with the whole gravitational wave business, that the merger of two compact objects is thought to have resulted in the discovery of gravitational waves. And so is there a relationship then between gravitational waves and gamma ray bursts? Well, it turns out there has been one observation of a gamma ray burst in 2017, one of the first gravitational wave events, in which we can associate that, we think, with a gamma ray burst, a weak but very short gamma ray burst. And I'll play this for you. Hopefully you can hear the audio on this. You have the increasing frequency of the gravitational wave emission right up until the merger, and wait for it, the gamma ray burst. So I'll run that one again. I don't want you to miss it. But you've got so again, you've got the increasing frequency of the two neutron stars as they merge, as they approach one another and merge, followed, oh, I didn't want to do that again. There we go. Followed by the gamma ray burst. So we do in fact believe that there is a connection between gamma ray burst and gravitational wave events, at least short gamma ray bursts. I will add that this is really the only good case for an association between gravitational waves and gamma ray bursts. So one of the goals of gamma ray burst astronomy is to identify additional counterparts like this one. Okay, so one of the things about these jets of emission, and you know, astrophysical jets are pretty ubiquitous throughout the universe. You know, but understanding their nature is still a bit of a challenge. We think magnetic fields play an important role in astrophysical jets. The jets in GRBs are ultra-relativistic jets. They're, again, the most energetic jets that we know of. But the magnetic field, we think, plays a role in terms of collimating those jets as a result of, you know, the rapid rotation of those magnetic fields, you know, wrapping around one another in kind of a helix fashion. And one of the things that we expect to see out of that is that if in fact we're looking at a magnetically dominated jet, we expect to see a polarization potentially. So in the canonical view of a twisted magnetic field, which you see here on the left, the magnetic field lines wrap around one another. The magnetic field is largely toroidal. I always struggle with that word, toroidal. And so, you know, if the observer sees this whole jet, one expects any polarization of the emission, say from synchrotron radiation, that polarization would average out to zero. However, in a relativistic jet, the observer sees only a fraction of this surface. They might only see this one region here, for example. And so in this one particular region, you see that, you know, the you can imagine here that the polarization is not going to average to zero, because in this region, the magnetic field is very well defined. So in this case, the net polarization would be positive. And so the model predicts large levels of polarization. This approach predicts large levels of polarization in all gamma ray bursts if the emission that we see is synchrotron. On the other hand, if the magnetic field is more disorganized, say from reconnection within the jet, then you may have a sort of disorganized structure here, in which case you may not see polarization of the emission. So all this to say that if we were able to measure the polarization of the gamma ray radiation that we see, we could use that to probe the magnetic structure in the core or near the central engine of the gamma ray burst. And that might help us to better understand the role of magnetic fields in these ultra-relativistic jets. So what we want to do is to measure, you might imagine, the polarization of the gamma ray emission. That's a little bit challenging. The gamma ray emission is prompt emission. You know, we never know when one of these gamma ray bursts is going to go off. We never know where it's going to go off. So it's really hard to catch that prompt emission in action well enough to be able to measure the polarization, even though we recognize that the polarization is potentially a valuable tool. But nonetheless, people have been attempting to do it. I've certainly been working on this problem for several years, more than I care to think about. But if we were able to measure the polarization of gamma ray bursts, we could begin to address several questions. What is, for example, the jet composition? Are jets matter dominated? In other words, is the energy being carried out by particles? Or is it Poynting flux dominated? Is the energy being carried, for example, by magnetic fields? What is the energy dissipation process of the jet? Is the energy being dissipated by shocks, internal shocks that are sort of flowing at different velocities and catching up with one another? Or is the energy dissipation taking place by magnetic reconnection? And what is the emission mechanism? We think it's probably dominated by synchrotron emission from energetic electrons spiraling about the magnetic fields within the jet, but perhaps not. Measuring the polarization in particular as a function of energy will give us a handle on identifying the radiation mechanism that is taking place. And then also we can use the polarization also to get a handle on the geometry of the jet and what in fact is the opening angle of that jet. So there's a lot we can learn by doing polarimetry. And several people over the years have made efforts to measure the polarization of gamma ray bursts using instruments that more often than not were not really designed to measure polarization. There have been some projects in recent years that have changed that a little bit, but this is a list of some of the early measurements. And you can see here, if you look at measurements of the polarization level of these jets, really don't paint a very consistent picture. 98% plus or minus 33%, 96 plus or minus 40, 43 plus or minus 25, 27 plus or minus 11. You know, these are marginally consistent measurements. And there have been a couple of recent experiments that have added this list. And, you know, but again, most of these measurements are on the order of, 2 or 3 sigma statistically, which is not a very convincing measurement. So what do we do about that? This is where LEAP comes in. LEAP is a large area burst polarimeter. Let me see what's next here. What is LEAP? We proposed this last year as a NASA mission of opportunity. It's a $75 million mission. It is a large area, wide field of view, Compton polarimeter. I'll get to that here shortly. It's a large area, so you have a large sensitivity. Wide field of view because you need to be able to monitor a large part of the sky to detect the gamma ray bursts. And it is a polarimeter to measure that prompt emission from the gamma ray burst. So it is designed to do polarimetry roughly between 50 and 500 keV. It does spectroscopy as well, between 20 keV and 5 MeV. So it's over a much broader energy range. Externally attached to the International Space Station. A launch date nominally of late 2025 in a minimum 2.5-year mission. So let's take a closer look. So this is, in fact, what the instrument or the payload looks like. These boxes here you see on the left, there are 7 of them. Each one is an independent polarimeter module. And then you have, so this is really the guts of the instrument. And then you have a couple of electronics boxes down here. One is the sort of central computer system. The other is an adapter box, which you really can't see clearly down here, but we have to take the 120 volt power provided by the station and adapt that to the 28 volts that we need on the instrument. There is also some shielding. This is effectively tungsten at this point in time, these brown sheets here. I'll talk a little bit about that more in a moment. This frame structure is a rather clever way of bolting payloads to the station. This is a mechanism designed by NASA. It stands for Flight Releasable Attachment Mechanism. Basically, you can plug these in, you know, kind of like, I don't know, Legos or something like that. So that once they plug together, you know, you get your electrical connections and all that taken care of. So it's a rather clever little system. The polarimeter module represents an independent unit. There's 7 of them, capable of performing polarization measurements. The design of these instruments derives from experience with the Great Balloon Program, which Kevin mentioned in the introduction, which we've been working on. We had the first balloon flight of that back in 2011 that you see here on the left. And previous Explorer class proposals. We've done some prototyping like what you see here for some of the previous proposals that we've done. So there's a lot of experience that has gone into this. But let me first start by talking briefly about how we measure polarimetry, or the polarization of an incident photon. We detect these photons simply by Compton scattering, scattering of a photon off of an electron. And it turns out that here on the left, you see a schematic showing a photon moving vertically downward. You see the electric and magnetic field of that photon. The electric field typically by convention defines the polarization direction, or the polarization vector. And as that photon comes down and it scatters off, this really doesn't quite show it, but it'll scatter off in the XY plane in some particular direction. And it turns out that scatter direction tends to be perpendicular to the electric field vector of the photon. So there's a preferred scatter direction in this plane perpendicular to the photon direction. And so if you map out and look at the distribution of events from, say, a gamma ray burst, if that gamma ray burst is unpolarized, that distribution will be uniform, as indicated here in the unpolarized red case. If, on the other hand, that gamma ray burst flux is polarized, it will have a distribution that will look more sinusoidal, as shown here in the black. And this comes right out of the Klein-Nishina formula for Compton scatter. So this distribution embodies within it both a signature that can tell you both the level of polarization and the polarization angle. So that's what we're looking for. So we design an instrument to measure this distribution, the scatter distribution. And here are a couple of results from our GRAPE instrument. These are measurements we made in the lab of photons in particular. The left one here is at 99 keV. The one on the right here is about 288 keV. So you can see what these polarization signatures look like in an idealized case. And we can define a figure of merit called the modulation factor, which really defines the efficacy of the instrument. So this is what the LEAP instrument module looks like. Again, there are 7 of these, but each one of these 7 modules consists of an array of 144 scintillation detectors, each with its own photomultiplier tube readout. So there are 144 photomultiplier tubes in each one of these modules. Some of these detectors are low Z material plastic, which is ideal for scattering photons at these energies. And some of them are high Z material, cesium iodide, which are ideal for absorbing photons at these energies. So what we do is we look for photons, events, in which we get a plastic signal coincident with a signal in one of the cesium iodide detectors. And we assume, and it's a pretty good assumption, that gamma ray photon scattered from the plastic into the cesium iodide, as you can see here on the left. Okay, so if we take a number of photon events that we measure in the instrument, and you can see a number of them here, plastic to cesium iodide, plastic to cesium iodide, and we plot the distribution of these scatter vectors, the direction of these scatter vectors, that's how we can get a polarization signature. Okay, so that's in essence how we do it. It's not a little bit more complicated than that, but that's in essence how we do it. So when we look at the events from the LEAP module, the polarimetry events are those that scatter between 2 elements. And here is kind of a, this is not showing a 12 by 12 array, but this is rather showing a, in this case, it looks like 8 by 8 array. Different kinds of events. We have a PC event from plastic to calorimeter. We have calorimeter to calorimeter, which can also tell us something about the polarization. And we have plastic to plastic. The singles events, we record those as well. The singles events give us a very good measurement of the total spectrum of the gamma ray burst. So we cover polarimetry between 50 and 500 keV that you can see here relative to a canonical spectrum for a gamma ray burst. And we cover the spectroscopically, we cover from about 20 keV to 5 MeV. LEAP does not have a sharply defined field of view. It's a very wide field of view instrument, but by its nature, the sensitivity falls off as you move off axis. But typically we maintain good response out to at least 60 degrees off axis. So we can cover a very large fraction of the sky at any given time. This is just a lot of detail here. This cross-sectional view of one of the modules shows the scintillation detectors, each of which has a photomultiplier tube, a high voltage divider board, a preamp board, and then there's 144 analog channels contained within this electronics down here. So again, this is modular. We can build up a sufficiently large area by assembling a number of these modules. 7 is the number we chose just based on our limits for mass and volume. This is one example of one of the individual scintillation detectors. Here you have the scintillator, and this could be either plastic or cesium iodide. The design is identical. There's a wrapping here of what's called vacuity, that is a reflective material that we put around the scintillator to make sure we collect the light. And then there's a housing of what's referred to as peak plastic material. Here is the photomultiplier tube, and then the boards go just underneath this photomultiplier tube. You can see them both there. Whoops, went too far. And then all of this is enclosed in a light-tight housing. Okay, so the LEAP concept here is that LEAP would be launched by a Dragon spacecraft. It would be launched in the unpressurized trunk of the Dragon spacecraft, transported to the ISS. And once it gets to the ISS, the arm would reach into the trunk and grab LEAP and carry it to its mounting point on the ISS. And then we'd begin checkout and operations. The operations, here you see a view of LEAP as it would be mounted at one possible location on the ISS, what's referred to as ELC3. But the operations here are very simple. This is a very passive instrument. It spends most of its time simply scanning the sky for transient events, looking for increases in the counting rate. Once a transient is detected, which typically might happen a couple of times a day, the instrument autonomously switches into a so-called transient mode to collect or to maximize the collection of data. And after a set period of time, typically a couple hundred seconds, it goes back into its scanning mode and continues on its merry way. So it's a very simple operational concept. There's very little user input required here. I should also mention that when we do get a transient, some of the data from LEAP is stripped off, and we send that to the ground immediately in real time. And it is then disseminated to the international community, both ground-based and space-based, to potentially follow up on observations of the gamma ray burst. Now, one of the other interesting things here, one of the other challenges, I'm going to show you this movie. This is an interesting time-lapse movie of an instrument that is on the space station now called the Neutron Star Interior Composition Explorer, or NICER. And this is a pointed instrument. And these black circles you see here are actually the apertures for the instrument. And let me start this up. It's got this freaky music. But you can see here it's scanning the sky, tracking sources across the sky, and you start noticing, for an instrument that's trying to monitor the whole sky, you can immediately notice one of our problems. As the station orbits the Earth and the sun moves through the sky, the solar panels have to track the sun. And so you can imagine that for LEAP, which is trying to monitor the sky, these solar panels are going to get in the way. So that's one of the problems that we have to face, we have to deal with. The solar panels are rather thin, but they can still attenuate and scatter the photon flux that we're trying to measure. There's another problem, and we call this our Soyuz problem. The Russians are ingenious, archaic. They have been using since the late 60s a mechanism on their Soyuz spacecraft. In other words, so when they're coming down on the parachute that you see here on the right, just before they hit the ground, because their parachute, it's not it's a parachute system that still results in a rate of descent that is rather high. So just before touchdown, just a meter or two above the ground, you can see here that it fires off some rockets and retro rockets. And so that tends to cushion the impact on the ground. So how do they actually trigger these retro rockets? Well, what they do is they take a very intense source of cesium-137 gamma rays to the tune of 1 curie. For those of you who are familiar with the intensities of radiation sources, that is a huge radiation source. And they have an instrument on board that looks for the gamma ray photons that scatter off the ground just before impact. And they use that as a trigger for these retro rockets. Well, that's all fine and dandy, but meanwhile, on orbit, you've got these 1 curie radiation sources that are generating a huge gamma ray background. And that is something that we've tried to work with. It really constrains us in terms of where we're pointing, where on the station we can be mounted. It influences our design of the instrument in terms of passive shielding that we have to use. For example, one of the sites that we're looking at is right here. This is the ELC3 site. And you can see there are 4 docking ports used by Soyuz. Typically, there's only 1 or 2 Soyuz vehicles docked at any given time, but there are 4 possible ports, and each port potentially could be a source of cesium gamma rays. So that's a bit of a problem. So here, looking on the station, here's the ELC3 site here. In the last few weeks, we've made a decision to baseline a different site down here on the Columbus module, but we don't yet have, we haven't yet upgraded our figures. So this still represents the ELC3 site, but this is where we're looking at now. Okay, LEAP was proposed last summer. We were one of 2 mission of opportunity proposals selected in March of this year for a phase A study. We have until March of 21 to produce a very detailed concept study report, and we expect a selection of 1 or 2 missions next summer. So they have 2 candidates. They will be selecting 1 or 2 of those 2 for flight. And if we get selected next summer, we would then move forward with the development, and we'd be flight ready in March of, or actually this should be September of 2025 now. So that's the mission. Let me then just briefly summarize the science objectives. We want to measure polarization. We want to probe the inner part of this jet and the role that magnetic fields play in that jet structure. How can we do that? Well, we can look at models, and they're really, in this interpretation, 3 general models for the gamma ray burst and the jet that originates in the gamma ray burst. And these 3 models can be defined as follows: synchrotron ordered model, synchrotron radiation with an ordered magnetic field, synchrotron radiation with a random magnetic field, and what's referred to as a Compton drag model with a random magnetic field. And so each one of these models predicts a different distribution of polarization values. So by looking at a population of events, looking at the distribution of polarization values, we can begin to sort of pin down to some extent which of these models is most likely. This is sort of a one-dimensional view here on the left. If we plot the polarization as versus this E peak value that I talked about earlier with respect to the spectra, we get this sort of two-dimensional distribution. The blue model here, the synchrotron with ordered magnetic field, shows some very specific structure in that distribution. But we can use this, again, in comparison with data from LEAP to begin to constrain the nature of the gamma ray bursts. And so each one of these three models can tell us something about jet composition, the role of the magnetic field, energy dissipation, and the emission mechanism. I don't want to it's getting late. I don't want to spend too much time on this, but suffice it to say that we can distinguish between these three different models. If one assumes that all gamma ray bursts follow one of those three models, we can distinguish between these three with a total of 65 measurements, 65 gamma ray burst measurements with a sensitivity level of 30% or better. That's what we're after. So we have a very specific goal to measure 65 gamma ray bursts. And then again, I mentioned this earlier, rapid follow-up to alert other observers to provide additional information to maximize their observations and to maximize the value of LEAP data. Secondary science, we don't want to just measure gamma ray burst polarization. We want to do other stuff. I mentioned and alluded that gravitational wave counterparts are certainly of interest. We have probably the most sensitive gamma ray detector on orbit. And so we will be able to measure very faint, very short gamma ray bursts, probably better than anybody. And so we will be able to collaborate with the gravitational wave observers looking for counterparts. And also for the solar people listening in, you may have noticed that the launch is 2025. That corresponds roughly to the next solar maximum. We expect to be able to do solar flare spectroscopy and polarimetry. Certainly the polarimetry will be better than anybody has been able to do in the past with solar flare polarization, which tells us a little bit of something about the nature of the electron acceleration process, the extent to which the accelerated electron population is beamed as it makes its way into the photosphere. So there's a lot of solar science that we can get from this as well. So 2025, you know, this is a nice view of the station. Hopefully by 2025, LEAP will be sitting right about here, studying gamma ray bursts and solar flares. And so I will leave it at that and happy to entertain questions. If anybody's still out there.
Great, thanks, Mark. Give people a second to come off mute. If there are any questions, feel free to speak up. Well, I guess, people are remembering their question. So you mentioned, Mark, assuming that gamma ray bursts follow one of three models, you can discriminate using 65 events. What if there could be multiple causes for gamma ray bursts? You know, what if the three models are valid sometimes and others?
Right. Well, that's certainly a valid question. And, you know, the point is that we can consider some hybrid distribution based on those 3 different model types. But again, you know, having those 3 models as kind of a basis for our study allows us at least to begin to look at the different possibilities that are there. It's as you sort of imply, it's not likely that all gamma ray bursts will fall into one of those nice, neat little boxes. They will probably be a variety. As I said earlier, if you've seen one gamma ray burst, you've seen one gamma ray burst. So it's a bit of a challenge in that sense. But in terms of, you know, when you go about designing an instrument like this, you have to design a science case that you can begin to attack. And so that is the science case we have. We can look and will look at different hybrid combinations of those. So by looking at that 2-dimensional distribution I showed, we should be able to better constrain the nature of the phenomena.
Thanks. Anyone else? Questions for Mark?
Maybe not.
Well, if there aren't any, we are exactly at 4 p.m. So thanks, Mark. Excellent talk. And we'll put it up online for anyone that wasn't able to attend.
Excellent. All right. Thanks, everybody.
Thank you.